Okay, yeah, so memorize. What I will tell you too is that technically 2 of these triples that I'm telling you are not triples because Pythagorean triples should be nice, pretty whole numbers. But there are 2 that I'm going to give you that I'm going to call triples, even though they technically are not, because they're just so important and we use them so often in trig. And they should sound familiar because you learned them in geometry. I put dashes between these numbers. If you would prefer to put commas instead, then that's quite all right. So the first one is 1 square root of 2. That comes from our 45, 45, 90 triangles, if that sounds familiar from geometry class. And then the second one is 1 square root of 3, 2. And that comes from our 30, 60, 90 triangles from geometry. Okay, so those are the 2 that are technically not triples that I'm still going to ask you to memorize. There are more Pythagorean triples than the ones that I'm going to give you here, but these are the ones that you see most often, and so these are the ones that I want you to have memorized. So 3, 4, 5, 5, 12, 13, 7, 24, 25, and 8, 15, 17. So those are the triples that I want you to memorize. And we're memorizing these mostly to save time and effort and energy on our part, because you will see these combinations of numbers so often that it will help you. Any right triangle that we are given, we know that we can do leg squared plus leg squared equals hypotenuse squared, right? You guys have learned a squared plus b squared equals c squared. You've done Pythagorean theorem plenty of times before. So I'm not going to work through that process necessarily. But the beauty of the triples is if you don't remember, you can always go back and use Pythagorean theorem. So here's why we learn these, and here's how they are used. If we have a right triangle, and so much of what we are going to do in trig class will involve right triangles. So if we have a right triangle and we are told that this leg is 5 and the hypotenuse is 13, then right away you should know, based on our triples, that this leg has to be 12. Okay, so the way these numbers are set up with what you are memorizing, the first 2 numbers are the legs, and the last number, if you notice in each set there, the last number is the largest. So that's your hypotenuse, because remember the hypotenuse is always the longest side, right? So legs are first, the 2 legs, and then hypotenuse. That's how those numbers are set up. Okay, so another example, if you are told, as an example, that this leg is 7 and this leg is 24, then right away, without having to do 7 squared plus 24 squared equals, take the square root to get what c is equal to, you should know that this is equal to 25. Okay? All right. These triples might be multiplied by a scalar also. So I'm going to show you some examples here. In other words, each of those numbers could be multiplied by 2 or by 3 or by 5 or by 10 or by a half even, right? So you kind of want to think about your triples and notice when you see right triangles to see if you notice that it's one of the triples that's maybe just multiplied by something. So I want you to look at some examples of that as well. So I've got a couple examples here. So let's solve for x first there. I'm telling you that it's a triple, that the numbers are just getting multiplied by something. Each of the numbers are getting multiplied by that. So I want to know which triple it is, and I want to know what x is equal to. Who's got that? I'm sorry? It is the 5, 12, 13. So this is 5 times 3, and this is 12 times 3. So this is going to need to be 13 times 3. So in other words, the length of that side is 39, but that's a 5, 12, 13 triangle. Okay, do you see that, guys? Each of the numbers, the 5, 12, 13, have all just been multiplied by 3. All right, what about, I'll keep that. What about letter B down here? It's also a triple. Does anyone notice what triple that is? That one's a little bit trickier because that 51 throws everybody.
8, 15, 17.
There you go. Good, CJ. So this is 8 times 3. This is going to need to be 15 times 3. And this is 17 times 3. 17 times 3 is equal to 51. So this is an 8, 15, 17. So side B, if we do 15 times 3, that gives us 45. Good. Okay, last one. Yep, that's a 3, 4, 5, right? This is getting multiplied by 4. This is getting multiplied by 4. So if we do 4 times 4, it's a 3, 4, 5. If we do 4 times 4, then y is equal to 16. Okay, so memorize those triples, and we will practice more with doing some right triangle, finding lengths of sides here over the course of the next couple of days also, okay? All right, guys, write what you need to on these. You may not need to do much. You may want to draw a picture besides writing information, but we need to review some info about angles. So what do we know about acute angles? Yep, so an acute angle measures less than 90 degrees. A right angle measures exactly 90 degrees, right? It equals 90 degrees. Typically, when we see that drawn on a page, we're going to see the little square in the corner to help us know that that's 90 degrees. What about an obtuse angle? Uh-oh. Do we not remember our geometry at all? Or are we just not awake yet this morning? Obtuse means it measures greater than 90 degrees. And what about a straight angle? That measure would be how much? 180. So it basically looks like a straight line, but really technically what's happened is that we've had a ray that we've rotated around exactly that 180 degrees. Okay. And then complementary and supplementary angles. Complementary angles, the sum is equal to how much? 90 degrees, good. And the supplementary angles, the sum is equal to 180 degrees. So you might be asked something as simple as just find the complement of 32 degrees, which just means we're doing 90 minus 32, so 58 degrees, or 180 minus 110, so 70 degrees. But I do want to go through some examples of kind of word problem types. So if you notice, for this one it says one angle of a complementary pair. So complementary pair means we are adding two angles together and they have to be equal to 90 degrees. And one of them is 3 more than twice the other. So 3 more than twice the other. I'm just going to call it X. But the key on these guys is remembering you need that other x in there. It's hard to remember to include another x when you're setting that up. So that's kind of an important part, right? So then we just solve. It's saying find both angle measures. So we've got 3x plus 3 equals 90. So 3x is 87, so x is 29. So that would be the first angle measure. If we double that, we get 58. 58 plus 3 is 61. So 29 degrees, 61 degrees. If we add those together, it does give us 90. So that checks. Okay. All right, somebody help me set up this next one. It's supplementary, so we know it's going to add to 180. John, can you help me with that?
She has to try 15, 3 times x, and is there another x too?
And then minus 15, good, and then the other x, yeah. So we get 4x minus 15 is equal to 180. So we get that x is, I don't remember, I'm checking my notes, 48.75 degrees. And so that means the other angle is 131.25 degrees. Okay, that should kind of be, I don't know, the word problem part of it might be a little bit new, but you should at least be familiar with complementary, supplementary angles. I don't know if you would have talked about standard position in geometry or not, but that's a very, 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 very important concept in TRIG. For a lot of what we are going to do, we're going to be talking about right triangles, but we're going to transpose these right triangles onto a coordinate plane to kind of visualize where these would be on a coordinate plane. So we're going to be talking about things in relation to where they are on the coordinate plane. So first, I want you to think about what an angle is, right? We talk about the fact that we have an end point or a vertex, and then we have a ray, and then we rotate some direction in order to create an angle, right? So that's the idea of how an angle is created. We have a point, and then we have a ray. We have a line that's going out from that. And then if we rotate that, then that creates an angle measure. All right, so for an angle to be in standard position, which is pretty much without fail what we are going to deal with or address in TRIG, the angles are going to be in standard position. So you need to be familiar with what it looks like or what it is. So an angle is in standard position if the vertex is at the origin, and what's referred to as its initial side, right? We started this ray here, and then we rotated and we ended here. So we're going to talk about what's referred to as our initial side, and then what's referred to as our terminal side. Terminal as in terminating or ending, right? So initial, that's where we're starting, and then we rotate, and then we stop, and at that terminal where we stop, where we terminate, that's our terminal side. Okay, so just a little bit of vocabulary there. So the vertex is at the origin, and the initial side is along the positive x-axis, along positive x-axis. Okay, a couple other things to remind you of that you may or may not remember. So remember, our quadrants are labeled, we start at top right, that's quadrant 1, and then quadrant 2, 3, and 4, right? So if you notice what it's saying besides this definition of standard position, which I'll show you some examples here in just a second, the other thing is understanding or remembering where our quadrants are. Because if you notice, it says an angle in standard position is said to lie in the quadrant in which its terminal side lies. So in other words, if we say that an angle is in quadrant 3, that means we are starting, this is standard position. We have a ray, its initial side is along the positive x-axis, and then we rotate to some place and it stops in quadrant 3. So that's an example of an angle in standard position that we would say is in quadrant 3. Because where it stops, where it terminates the rotation, it's in quadrant 3. Okay? All right, I just realized, let's review something here. Let's think about values in terms of the rotation here. If we're in quadrant 1, then our angle measures are greater than 0 degrees and less than 90, right? What about quadrant 2? It's greater than 90 degrees and less than, what is this line here? This place is at 180 degrees, right? Quadrant 3, it means it's going to be a value that's greater than 180 and less than 270. So I'm adding 90 again. And then quadrant 4 means we're greater than 270 and less than 360 degrees. Uh-oh. Okay, so if we say that we're talking about an angle that's in quadrant 3, then that means we've started at our standard position and we've rotated around somewhere between 180 and 270 degrees, okay? We're going to talk about adjusting that rotation here in just a second too, though. But let's look at some other examples. Let's go back to this. If I say that we're looking at an angle that is in quadrant 2, that means we're starting in standard position and we're rotating around to somewhere here in quadrant 2. And then for quadrant 4, that means we're starting here, we're rotating around somewhere to quadrant 4. Now all of these, the rotation, and I don't know if this is something you all would have talked about in geometry or not. I think so, but I'm not sure. All of those rotations are positive rotations. So it's on the next page that we're going to write and talk about the idea of a positive and a negative angle measure and what the rotation is, right? We could rotate still from this starting standard position. We could rotate in this direction. That's going to still end us up in quadrant 3, but this is a negative angle measure. This one here is a positive angle measure. So this one would be, I don't know, approximately 225 degrees positive. And negative, we would say that that's about negative 135 degrees. Approximately. So just keep in mind, we can rotate in the positive direction or the negative direction. And especially in quadrant 4, notice we don't have to rotate very far to get to where that ending place would be, right? Okay, so standard position along that positive x-axis, and then we are rotating either positive direction or negative direction. And we'll look at that here again in a second. Okay? All right. Questions, comments, thoughts? Something that I need to clarify for you or explain? Okay. This first part's just a little matching thing. We've got 3 terms on the left. We've got 3 explanations on the right. We're looking for, one of those is, it says a fixed endpoint that joins 2 rays. Which one of those on the left is that? CJ, a fixed endpoint that joins 2 rays. Is that a vertex, initial side, or terminal side? That would be the vertex, good. And then the ray that rotates, and then the fixed ray. So the wording of that's kind of weird, but I think hopefully you can pick up on that. The ray that rotates, is that terminal side or initial side? Maya,
It's the initial side.
the ray that, when it rotates. So once it rotates, it stops somewhere. So good, then that's the terminal side. So the fixed ray is in other words, where it's starting. So that's the initial, right? Okay, so a little bit here where it's talking about positive and negative angles. So the measure of an angle, it tells us direction and amount. So positive angles, we rotate counterclockwise. If you think about it, it's because of our quadrants, right? If we are starting in that standard position and we want to rotate into quadrant 1, and then quadrant 2, and quadrant 3, and quadrant 4, right? We have to rotate up. So that's counterclockwise. So negative angles, they have a clockwise rotation. Okay, and then somebody see if you can explain this in your own words. Don't go back and look at what I wrote, but see if you can explain what does it mean for an angle to be in standard position? What do we need? What do you think, Sam? Try. Okay, go ahead. Yes. Peek back.
So the vertex has to get its origin where it started, and the initial side has to be in the positive x-axis where it was counterclockwise, not clockwise.
Okay, initial, well, it can go counterclockwise or clockwise.
Clockwise goes negative.
Yep, but it can rotate either way, right? Okay, so an angle in standard position, vertex is at the origin, initial side along positive x-axis. But then we can rotate either way, positive or negative, right? Along positive x-axis. Okay. Some other terminology to be familiar with, and this is, if I've got it listed down here also, if you notice, it's what's referred to as a quadrantal angle. It's kind of a weird word. A quadrantal angle is an angle in standard position whose terminal ray lies along one of the axes. So in other words, think about the lines that create the quadrants, right? So it's the 90-degree angle. It's 180 degrees. It's 270. And it can also be 0 degrees. In other words, it starts there, but it never does any rotating. You can think of that as 0 degrees, or you can also think of that as 360 degrees. You need to be familiar with both of those. Okay? Let's think about this also, because those are the main quadrantal angles we're going to talk about. 0, 90, 180, 270, 360. But I want you to think about the fact that we could also refer to this quadrantal angle as negative 90 degrees and negative 180 degrees and negative 270 degrees, right? So quadrantal just means it's stopping at one of those axes. So the main numbers we're going to be thinking about are that 90, 180, 270, 360 business. But it could rotate negative also. So you have to kind of keep that in mind. Make sense? I know it's a weird term, but hopefully the quadrant part of it usually helps people remember that. Okay? All right, here's where we need the calculators a little bit. We are going to talk about converting. So here's the deal. You guys have learned about degrees. You measured degrees, at least you should have, in geometry class, right? Degrees can come in smaller units, and that's what we are going to look at, is how we deal with those smaller parts of a degree measure. The nice thing about it is that we use words that we're familiar with, so it makes it a little bit easier to think about. So if you notice, the smaller component to a degree is minutes, and then the smaller component to minutes is seconds. So that part of it's kind of easy because we already know there's 60 seconds in 1 minute, there's 60 minutes in 1 hour, only now in this case we're talking degrees. So 60 seconds is 1 minute, 60 minutes is 1 degree. So those are the smaller parts, is the minutes and seconds, smaller parts to a degree. So you need to be familiar with the symbols here. So if you notice, this is saying 60 minutes, that 1 tick mark that represents minutes is equal to 1 degree. And then 60 seconds, notice there's 2 tick marks there, so that's seconds, is equal to 1 minute. Okay, so those are the smaller components, or how we can break up a degree into smaller pieces. All right? Okay, I lost my degree symbols when this got typed in a formatting issue, so just make sure you put little degree symbols there. So we need to, because it depends on whether you're on a section of your test where you are going to have your graphing calculator or not have it. So you need to know how to do this with like a basic calculator, or just basic calculation. And then I want to show you how you do this on the graphing calculator also. So if we are converting, if you notice, if we have something like this, this is saying we have 58.745 degrees. So we have 58 full degrees, but then we have 0.745 of a degree also. And we want to convert that into degrees, minutes, and seconds so that we can think about how much that is, right? So the process, if you notice, is that we multiply the decimal portion. So just this decimal portion, that 0.745, if you notice, gets multiplied by 60. At that point, notice this 44, that's the number of minutes that we have. But then we take that 0.7 that we got as our decimal in that answer, and we multiply that by 60 again, and that gives us our, that gives us our seconds. Okay, so this part is for our degrees. I thought I was in highlighter mode, sorry. Let me try that again. This is our degrees, right? We take that whole number part and we put that in as our degrees. But then we take the decimal, multiply it by 60. The whole number part that we get for that becomes our minutes. And then we multiply that decimal times 60 again. Guys, I need you to notice something. The seconds might have a decimal in it, okay? The minutes should not have a decimal, but the seconds might have a decimal, so just be conscious of that. Okay, we're going to practice this process here in just a minute. But that's the process. You just take that decimal portion, multiply by 60, take this next decimal portion, multiply by 60 again. That's decimal degrees to degrees, minutes, seconds. If we're going degrees, minutes, seconds, so notice what we have here. 124 degrees, 18 minutes, 26 seconds. If we want to convert to decimal degrees, guys, you've got to make sure you have your float 12 on, because on your My Math Lab that you're going to do to practice with this, it's asking for like 4 places after the decimal. And couple people in my first period class, they weren't getting the right answer because they weren't rounding to the right place. So if you notice, if you think about it, because minutes, there's 60 minutes in 1 degree, it's going to be out of 60. Because there are 3,600, in other words, 60 times 60 seconds, then whatever the seconds are, you put over 3,600. So guys, you can plug this in as one whole amount there on your calculator. 18 divided by 60 plus 26 divided by 3,600. Just put that all together. I'm showing it separate just so that you can kind of see the different parts. But when you put it all together, that's what you're going to do for your decimal. Okay? So look at this one, the 16 goes over the 60, the 36 goes over 3,600. Add that decimal together for that part. Okay? All right, let's talk about how we do this on the calculator. I've shown you some screenshots, but I need to show you how you get to these. So let's practice this process. And I have to kind of peek over a shoulder or use a calculator to talk you through this. Let me make up a problem here. Let's do 192.675 degrees. And then let's do 215 degrees. I don't know. Okay, I'm just making these up off the top of my head. Okay, to convert, if you notice on the left-hand side, I've got decimal degrees, so I want to convert to degrees, minutes, seconds. You're going to find on your calculator that right there. So let me talk you through how you're doing that. So you're going to actually plug in that 192.675. I'm sorry, make sure you are in degrees. If your calculator is in radians, make sure you switch it to degrees or you're gonna get a really weird answer. So top right corner to check to see if you're in degrees or radians. Give me a second. You're in degrees, so you're good. Top right corner tells you radians or degrees, and if you just click on it, it'll toggle back and forth between them. Yep, use that one. So make sure you're in degrees. Is your name on that, sweetie? Yeah. All right. And then type in that 192.675. Okay, and then you're looking for, it's called the catalog key, but it looks like the book. So it's right underneath the delete or clear key. So hit the book. And then you have to kind of arrow down to that DMS, or you can actually, like if you hit the D down at the bottom, that'll get you to the Ds in that list. And then you can arrow down and hit that DMS. And then once you have, once you're highlighted at that DMS, if you hit enter again, it'll give you your answer. So you should have 192 degrees, 40 minutes, 30 seconds. Who needs help? Okay. You are in, yeah, you're in some weird, okay. And you want to be on that first tab. See all of those different tabs there. Make sure you're on that one. And then you can go to D, and you can arrow down. There we go. And then enter, and then enter. The beautiful thing is that, guys, it's gonna stay there in that place until you move it. So that's nice. Did everybody else find it? The DMS? Okay. To convert the other direction, if you have your graphing calculator, you have to be able to plug in those degrees, minutes, and seconds. So you want to go to that sideways smiley face key. In other words, that template key that is just to the left. It's the left toggle next to the book. And then if you notice, left, it's the second column, second row. So your sideways smiley face key. Second column, second row. So you just want to arrow over to that. There you go. Yep. Oops. Uh-oh, something's wonky. You didn't. Yeah. You gotta. Okay. That's clear. Okay. Start over because you've got to do. Nope. Back up. Escape. You got to put. Oops. All right, Maryland.
I got a fraction.
Oh, on your, that's interesting.
If I do that.
All right, on some calculators, it's second column, second row, and on
15.
others, it's not. degrees, minutes, seconds. So click on that, and then that will fill in, and you just have to autofill.
Do we round to the nearest hundred?
You don't want to round too much. And like I said, I'm getting a fraction. If you get a fraction, hit your control enter to get the decimal. It looks like mine is rounding. What are you all getting? Are we just getting 0.41? Even if, I'm trying to write way too fast and I'm slipping all over the place. I'm not used to writing on this. It's been a while. All right, it looks like we just get 215.41. Or did it go farther than that? Okay, so mine is not set for my rounding. Oh, wow, yeah. Okay, you need to fix your calculator too, in other words. Talia, can you read that out? It's 215.409 something.
7, and then a bunch of 2s.
A bunch of 2s. Okay, so we'll do that. Degrees. So yeah, you're rounding. Please make sure your calculators are on float 12. Because like I said, on the MML, it's going to ask for 4 places after the decimal. Okay, can I help somebody with either of those or with changing your float? Okay, guys, try these problems. We'll go over them in just a second. Work with your neighbor, and if you don't have a partner with you, then if you two want to work together, you can. All right, what did we get? Dina, what'd you get for number 1? Yep. 46 minutes, 12 seconds. Sounds good. Sophia, what'd you get for number 2? 1325 degrees. Good. And then Lucy, what'd you get for number 3?
Negative 154.795 degrees.
Good. We don't really say that 0 is negative or positive, but guys, this is like we're rotating not quite 1 degree in the negative direction is what that's saying. So like you don't really need the 0 there, but some of you may want that just to kind of help you think about the fact that there's no degrees here. It's just that other little bit here. So it's really just a negative 55 minutes and 21 seconds, right? But if you want to put the 0 degrees there, you can. But it looks weird to see a negative in front of a 0 like that. Okay, what's the angle measure for number 5? Owen, what'd you get for that? 350, good. A couple of ways to think through that. You can either think of this as 270 plus that 80, or it's 10 degrees, right? 80 plus 10 has to give us the 90 degrees. It's 10 degrees less than a full rotation, so it's 360 minus 10, so 350. Good. Zach, what'd you get for number 6? Yeah, negative 250 degrees. So 20 degrees less than that rotation up to 270. All right, 280 is going to look like this. We're going to start at standard position. We're going to rotate to 270, and then we're going 10 degrees more. So it's going to look about like that. 710, guys, that is 10 degrees less than 2 full rotations. So you've got to show that you're rotating once around and then coming all the way almost to there, basically, right? So yes, we are going to talk about angles that rotate more than 360 degrees, and we'll deal with that. I don't know, do we need to do some more review or practice with complementary and supplementary angles, do you think? Let's just set one of these up maybe. How about this one? 2x minus 2 plus 3x plus 7 is going to be equal to, in this case, 90 degrees. And then you would solve from there and figure out what x is. And then make sure you go back and find your angle measures, right? this is more practice similar to what we did there, so I'll hold, I don't know, what do you think? Should we go over one of those, or are you good? I think you're good. Okay, I will have the full written notes online if you want to try those and check your answers. Let's look at these last three, though. These are Pythagorean triples. Okay, actually, let's do this first. Okay, so all of these are Pythagorean triples that have been multiplied by a scalar. So I want to figure out what is A equal to, what is B equal to, what is C equal to, without doing Pythagorean theorem. So for number 5, what is A equal to? Somebody call it out.
15.
15, how do we know that?
Because it's a 4, 5, and that would be 3.
Okay, so 3 times 5, 4 times 5, 5 times 5. So it's a 3, 4, 5. Good. Excellent. What about B?
Is it 26?
Okay, good. How did you get that?
Take a 5, 12, and 13.
Okay, so this is a 5, 12, 13. Each of these is getting multiplied by 2. So 13 times 2 gives us the 26. Good. So B is 26. And then what about C? 24. That I'm repeated that 51 to help you remember that 17 times 3 gives us 51. So this is an 8, 15, 17. Each of those is getting multiplied by 3. So that means that C is equal to 24. Excellent. Okay, so you've got to be memorizing. That's part of your homework. The other homework is in my math lab. It's not due until Sunday night at 10, but you have time to get it done, and you're going to have other homework that's assigned tomorrow, so I would suggest getting as much of it done as you can. You've got about 15 minutes, so you could probably get it done, or at least close to done.